Hey, welcome back to this new episode. In this video, I'll talk about numerical integration using a trapezoid rule in Python. So we will write a simple script in Python that explains the algorithm of trapezoid rule, and we will then perform some integration on a certain function between the limits of a and b, and I will consider a given number of points. So trapezoid rule basically considers a given number of points, and then we need always to find the stepping interval h, which is usually the length or the height of each panel subdivided in between the interval. So, and each corresponding x is given by the lower limit. I is just iteration number from maybe 1 up to n, and then we have b as the upper limit. So the algorithm basically simplifies to this expression, as you can see. So when we have a given interval a to b, we can subdivide this interval into a given number of panels or trapeziums, each of a given x coordinate here, as we have seen, each one computed based on this formula. And then finally we sum those up, all of them, and we can see that the first f1 and the last one take on weights of h over 2, and then the middle functions simply take on a product of h and themselves. So what we basically see is that within these weights we have h over 2 and h over 2 at last, and the mid terms only are multiplied by h. So what you're going to do before we go to this further, we need to look at what function we are going to integrate. In this simple example, we'll be integrating a function exponential of minus t. But before we go further, let's look at in Excel how this is how we can consider that. So in Excel, basically what you are looking at a given number of points n at a given interval ab, and then I is going to be changing from 1 up to n number of points we choose. Okay, the x coordinate, as we have seen, is going to be xi equals a, the lower limit, plus I minus 1 h. Okay, now the h is given by b minus a over n minus 1, because there will be n minus 1 number of panels within that interval. And then finally fxi is the function computed at a corresponding x value. So now let's look at when I equals 1. So we have this one 0, and then we have a, which is the lower limit, and then when I equals 2 we have that, until we have 8 equals 7h, and then n minus 2 we have that, and n minus 1 that, and finally n we have xn equals a plus n minus 1 h. When you look at this, this is the upper limit, which is fixed, and the lower limit, which is fixed. So we have some stuff changing in between here from x2 up to xn minus 1. Okay, so when we generate the corresponding function, the corresponding functions, we can see that we have f1, which is our fa, and then they are changing based on the x until fn, which is the same as f of b. So basically what is changing is in between here. So what you're going to do is to basically look at what is constant, which is the first f1 and the last f1, which are not changing, and then group that as our sum, initial sum, since it's not changing. And then we can look at what is changing, and then we can write a simple loop in Python that caters for these changing x's. Okay, so now when we go to Python Jupyter Notebook, we'll begin by defining a certain function that will always return the expression we are going to integrate, which is or the function we are going to integrate, which is exponential minus 2. So before we define the function, let's try to import the packages that will be used to do the computations and plot. So the target basically is to do the computation of the integration, and then finally we can look at a relative error and how we can look at how the error is changing with respect to n as it is changing the number of points. So that means we need to do some plotting, so we need some package that will plot. So I'll begin by import matplotlib.pyplot as plt, also from numpy import everything. So when we do that, after importing these two packages are just enough, we'll go further and define the function in terms of t. Okay, this function is to return exponential of minus t. Okay, so whenever I call fn, it returns exponent minus t. I'll go ahead and define also what I can call exact in terms of t. This is a function that will try to return the exact integral of exponential minus t, and this is to return exponential minus exponential of t of minus t. You can see that when we integrate exactly exponential minus t, we get minus exponential of minus t. So that is well set. Now we can then further go ahead and write the function for the trapezoid. So I can say define trapezoid, and this function, as we have already seen, will input the lower and the upper limit, okay, and then our n, which is the number of points. So if we go down here, like I already mentioned, there's some stuff that is not going to change, which is the first one and the last one. And also if you visit back the algorithm, you can see that the first one and the last one, these two are multiplied in by h/2. Okay, and then so I can now go up here and introduce my sum trap. Okay, and this is equal to, so I'll make a call of this function fn of the first, then plus fn of the upper limit. Okay, and as we can see, this is divided by 2. So I'll first ignore the h, I'll multiply it later. So this is our first initial sum. Okay, so which means that we have now a task of summing up all what is in between here. And like I already mentioned in this expression, these remaining terms keep changing. You can see that this is h, 2h, 3h. So it's like this is 1h changing from here up to n-2. Okay, so now we need to write a loop for these two, I mean for all these terms that are remaining, since we have already catered for this one and this one. So how to do that? First of all, as you can notice that we have not defined our h, which is the stepping interval. So I can also, it is a constant, I can keep it here, h equals b minus a everything over n-1. Okay, so that is well defined. So now let's go to write a loop for, I can say for I in range of 1 to n-1. So the reason why I'm doing that, if we visit back our Excel, you can see that since we are looking at this part here, the h itself is changing from 1 up to n-2. Okay, so n-2, that is why I'm ending at n-1, because Python does not consider the last or the last limit. It will only stop at 1 less, which becomes n-2. Okay, so then we'll have captured all these details here, all these functions here. So now let's go ahead by, we need to keep summing up all of them. So I will go down here under the for loop and say sum, okay, that is sum trap plus equals, this simply means that I'm starting adding from the upper sum, which is a constant. So something that is changing, I'm calling my function that returns exponential minus t beginning from a plus I can put this in brackets, I times h. Okay, times h. So as you can see, under this function we go up here and it's like our t is now, or what we called previously our x, is equal to the a plus I h. So in other words, this will generate for I equals 1, this will be a plus h, I equals 2, a plus 2 h, and so on. That means by the time we stop at n minus 1, we will have captured all these details. Okay, so now let's proceed down here, and we need to sum everything and multiply it by h over by h. Okay, so now this becomes sum trap equals, then we are multiplying by h, so this is equal to h. Okay, so that means this sum is now multiplied in by h. So then we can say return sum h. Okay, sum trap, that's what we need to return. Okay, now this is the function that will always perform the trapezoid rule according to the algorithm, but we need to see what happens when we change n, what happens to the error, what type of error we are making, how much is that as we change n. So we are going to go down here. In this first trial, we'll try to set the a and b to be fixed, otherwise we can choose to be calling the function and we input the values of a, b, and then n. But in this case, let's try to just fix the upper limits and the number of points. This is up to 1, and then let's look at our n that will keep changing to maybe 300. Okay, okay, let's try 200 at the beginning. So now what we need to look at is that we wrote our function here, which is the exact function. So I need to get to know what is the exact sum. So I will say exact sum equals, then I need to simply call my function exact of b, take off exact at a. So we are evaluating the integral at the upper limit and a lower limit, and then that will return our exact sum. So when you do that, then finally we need to go down and say for, let's say, j in range of 2 minus n. Okay, then we need to see how the trapezoid is changing. The error in trap, okay, just use that, because we'll have an absolute value of that positive number. We have the trapezoid, which I'm calling now trapezoid, that returns the value of a, b, and then now the n, we need to keep changing to see how the value is changing with respect to the number of points. We need this one since it is the one that is changing. So that is j input. Then this is supposed to be minus exact sum. Okay, and then this is over exact sum. Okay, and all this is supposed to be under. Okay, so let's look at the, okay, so that means I need one more bracket here. Okay, so that's the error. Now we need, for simplicity, what I'm going to do is to create here an empty set, empty list of er, or I can call it et, equals empty list, where I want to append all my error values, and then also I can call this one it, where I want to append all my n values, j values for n. Okay, so now I can say et dot append ert. So that means for whatever value I calculate here, I drop it here, okay, in et, and likewise it dot append j. Okay, when I do that, then I can go down here and try testing to plot. Okay, I imported as plt, so plot of it and then et. Okay, then I can go down and say plt dot show. Okay, so now if let's try to run that and you see what comes up. It is still busy, and then it is returning figure size with so I run it again, and then this is what we have. Okay, so basically this is we can try to linearize this a little bit more and see how linearly it is by plotting this on a log plot. So I will say plt.log of it and then et. Okay, when I do that, run it again, it should give us a straight line. Okay, so you can see that it is changing linearly with the plot of relative error, and as n is changing. So while you are changing n in trapezoid, the error is decreasing linearly. So then we can let's try to visualize some of our results. So I'll go down here under the rope and say print. Okay, we need to print some results for j, and then I'll create some space for t, make it a tab, and then we need also to look at the trapezoid itself, the results produced. So I'll have that a, b, and then j. Okay, then a comma, and we have some again tab to make some space. Then we can print out the relative error, and this is ERT. Okay, so now this is what we have. If I do that, it will do some plottings down here. Okay, but you can hardly understand this clearly. So what you are going to do is to make it more, explain it more by printing the headings. So I can print my headings like this. So the first one is n. Okay, and then I'm creating a tab to skip some space, and then likewise the second one is trapezoid area. Okay, a space again, and then that's for t, and lastly we have relative error. Okay, so if I do that, I need to make some space below. So if I run that, let's see. Okay, so you can see that the first one represents n, and the next one trapezoid area, how it is changing, relative area, and then you can see that down here it ends with this. But now we need to see exactly what is the exact area. The exact area, remember we wrote our function for the exact integral, so I can print that out as well from here, that the exact area equals, okay, we called it exact sum, right? So now we have exact sum, so it will be printed down here, but then I need to create some space below that. So okay, and then you can see that we have this exact number, the same as our exact that. We can try to do some bit of formatting of these numbers. Basically, by formatting, I'll format that to shift that point maybe 4 decimal places and in exponential form. This same stuff, same formatting, I can copy that to what we have here. Okay, 4 decimal places and in exponential form. The same I would like to do for the exact sum, and if I run that, you can see that the numbers are looking a little bit sweeter. And then for the above here, I think remove the formatting. Okay, relative error, like that. So if I run that again, to be kind of, this is for the trapezoid area and this is for the relative error. You can see how it is decreasing until down here where n is stopping. We have this 6.30, the same as that. Okay, so you can see that the area is becoming more accurate, and as we move, as n is increasing, and the error is decreasing more and more as we move further. So for the plotting, I can just make it to look more beautiful, maybe by say plot period.title, and then say that a plot of relative errors versus n. And then finally, I can also label the x-axis period.x label, and that's n. Okay, a number of points. And then I can say period.y label, we have that as relative error. And then finally, I can try to put some grid on period.grid. Okay, so when I run that, it will look more nicer. Basically, I can make the plot larger if I say period.figure. Okay, and then we have fig size equals, maybe I can keep it as 12 and length by width and maybe 7. So if I do that, the figure will be a little bit bigger. Okay, so this is how we can look at the how the error is changing with respect to n for the trapezoid rule. Thank you for watching. Next time I'll come back with another video about Simpson, and then we'll compare the Simpson and then the trapezoid and how the relative errors are changing.